Hi, I'm Sandesh from Juniper Networks, and I'm here to present Juniper's strategy and use cases which we have tried to incrementally insert P4 on our platforms. So in Juniper, we also struggle with the same problem which Alan from Manox talked about and Mario Baldi touched about, how to incrementally insert changes or new portions of the P4 into the existing devices. So in Juniper we have large customer base, and we build our platforms on various targets, various ASICs. So we have the same problem which Alan talked about, that how do we map P4 to various targets which we have. And also at Juniper, because we already have our product deployed, we don't want to just rewrite everything in the P4. We just want to take baby steps to introduce P4 into our devices. So this talk is about our strategy and the few use cases which we have tried internally. So this is the agenda. I'll talk a little bit about motivation. Mario actually already talked a little bit about why we actually need incremental insertion. So I'll talk a little bit about motivation and then introduce the AFI, Juniper's Advanced Forwarding Interface for data plane programmability, because AFI is the magic which we use to support P4 on our platforms. And then I'll quickly go through the first two parts and then try to spend a little bit more time on the use cases, and then tell a little bit about our announcement which branded 2 days ago about Juniper being part of the Stratum. So I'll talk about what we are actually bringing into the Stratum. And I'll try to quickly go through the slides, and so that if you have any questions, I like questions more than actually presentations, so I will like to spend some time on questions as well. So motivation is, so existing networking devices have their code base which has been there for a long time. They have implemented so many features. We don't want to rewrite whole features, all the features which we already have deployed, and nobody would want to do that. At least it doesn't look good thing to do. And even if let's say we have provide a box which supports P4 and runtime and everything, right? Many of our customers may not want to actually take the control ownership of the control plane. I mean, hyperscalers like Google, they have the software teams which can handle any complexity which control plane can control plane should involve, right? So we have small customers, big customers. So we don't want to we want to give a complete solution and give all the flexibility, and they will deal with only the problem which they actually want to deal with. Let's say they want to talk to our control plane or talk to our data plane, right? So we have I'll talk about where all we can program our stack or our devices, and then I'll talk about, because this is data plane, about P4, so I'll spend more time on the P4. But I will also bring in some of the points which are needed from control plane programmability, so that to complete the talk, right? Because to give some solutions we have to involve what we have in the control plane and what we are giving the data plane. So I'll go through these slides quickly, because everybody I think here knows about it. So every networking device, big or small, has logically 3 layers: control plane, data plane, and management plane. And here I'm mentioning only the technologies which Juniper currently which are relevant for this talk, right? So between control plane and management plane, we have CLI, SNMP, Netconf, GNMI, GNOI, OpenConfig, streaming telemetry. And in Juniper, to program control plane, we have a JET. JET is the full stands for Juniper Extension Toolkit, and I'll talk about a little bit about it. So in my talk, you will definitely find the details about the technical implementation, not this jargon about what it is not, right? So JET And then in data plane, we have our AFI, and we are trying to introduce P4 incrementally to our customers or to our products to support P4 using AFI. So what's AFI? So AFI, this is a 10,000 feet view of the layering of AFI. At the top, we have controller. Then we can write AFI client using AFI, and below that, we can bring in our forwarding toolkit or merchant SDK to support our platforms, which are built on merchant SDK. And then below that, we have forwarding ASIC. So it doesn't give you all the details, but this is the how broadly it looks like. Little bit more detail here. So AFI is the interface which we use to build clients, third-party clients, which customers can build or we can build for them, and internally we use for Junos. So all the features which we have implemented in Junos also use AFI internally. And below that, we have Aft forwarding toolkit, which actually supports AFI. And below Aft, we can support custom or merchant silicon, and we have management side of the whole infra and the host interface for packet inject and packet punt. And then we have silicon, the drivers, silicon, and the fib tables in the silicon, right? So this is the little bit more detail about how the AFI layering works. Little bit more detail about the AFI. Okay, so what's AFI? So AFI is Juniper's way to model the forwarding plane, right? So how P4 looks at the forwarding plane is mass action pipeline and few more things, right? In Juniper, we look at forwarding plane as a graph of AFI objects. So it's we want to make it so flexible so that it can be easily mapped to all our targets, and also easy enough for anybody to actually program using AFI. So these objects which we have come up with, which we are actually at a level not too target specific, but not way too high level that you actually struggle to actually map them to actually the data plane, right? So I'll give you some few examples of that. I cannot cover all the objects and details of AFI objects. If you're interested, you can catch me after this presentation. We can talk in detail. So this is very rudimentary examples of AFI nodes. So each AFI node can point to next AFI node, and if you want to somehow implement semantics of if and else, then you can use an object which does some comparison and jumps to one or the other AFI node. So this is the simplistic view. So in the next slide, little bit more detail, right? So let's say if you want to implement the switch statement in these objects. So here we are using AFI op object, AFI index list object, and AFI field object. So the three objects using this, we are implemented switch statement, right? So AFI operation takes two other AFI objects to compare them, and actually does some operation and copies the result in AFI field type of object. And that AFI field type of object can be used by next AFI index list, which it just looks at what is the value and jumps to that index, and it goes to that object which is at that index. And then we have another AFI object to match next case statement, and then we can jump to another one, and then so I think it's not that difficult to, so that I need to explain each and every this one. But idea is that sys statements, to give sys statement can be represented in these AFI objects, and if you implement just this AFI objects, if you look at the AFI, there are only handful of them, and you just implement those in either microcode or in FPGA, or you can map to your target ASIC. It will be very easy to actually realize any pipeline which you can represent in terms of these objects. Okay, and I'll talk about sandboxes. So sandbox is a virtual container inside the forwarding ASIC, and it has some virtual ports, and there's a graph in between, and there's a virtual input ports and virtual output ports. These ports are virtual; they are not actually physical. They can map to either a physical IFD or physical or logical IFL, or they can even map to a firewall action or a route. Route can point to the input port, right? So these are virtual. And sandboxes can be either chained, they can be nested, or they can they can use in a slice format that only some of the ports can be handled by one of the one sandbox, other set of sandbox ports will be handled by another sandbox. So with AFI, all these things are possible, but keep in mind that this is not possible in every hardware, but in some of them they are possible. So it's possible if, let's say, in our Trio Penta silicon, it's microcode based. All of this is possible, so we actually use them heavily in that. For the use cases which actually we need for customers who are using our MX series boxes, and they need some features which will, can be implemented using this sandbox architecture. Okay, to give you a little bit more detail, so sandboxes can be chained, and different sandboxes can be controlled by different control plane. So here, just to give you an idea, that one sandbox is a default sandbox is controlled by Junos, and we can also bring in new sandboxes which is created by our AFI layer. One sandbox can be controlled by P4 controller, and other sandbox can be controlled by Psi. And we actually, to support Psi or Stratum, we just we bring in our AFI layer below them, right? So AFI layer is flexible. The idea is that you have some way to represent something, break into very small pieces, and then combine them again to map to the primitives which actually your hardware supports. So I think I cannot cover all the details here, but I think it's if you are interested, we can talk about it after the presentation. Okay, so this I talked about earlier. So Juniper supports builds platforms on mainly 3 types of silicon. We have our merchant custom silicon, which is truly flexible. It's Trio/Penta. Penta is our actually next version of ASIC, which is in the Trio line of ASICs, and which will be releasing our Silicon cards based on that very soon. And we have fixed function ASICs. One of the example of that is ZX. And then we have merchant silicon. We build a lot of boxes based on Broadcom also. So we have this lot of targets which we have to support P4 for, right? Because our customer doesn't want to deal with what platform we are building on which target, right? We have to give them a common interface which they can use. So this is a little bit about how we support Stratum and P4 in Juniper. So we have every vendor has to write P4 compiler backend. So we have also written it, and it translates the switch.p4 into our let's say the P4 program into a blob, which is nothing but a model of same P4 program in the AFI format, right? And then we give that file to our JP4 agent, which gives that to AFI layer. AFI is HAL layer, AFI HAL layer. There we understand this format, and below that we have merchant SDK. We map those objects to that SDK calls, which we will realize those objects into the SDK, into the actually ASIC. So this is how it's supposed. A little bit more about JP4 agent. So we have the top, we have Stratum, which actually nothing P4 runtime server, which handles P4 gRPC RPCs from controller, and below that we have AFI is actually HAL layer, and below that either we can have AF toolkit or we can bring in merchant SDK from let's say for us we are trying to support P4 on one of the box which we build on Broadcom silicon. So we are using this model for that. Okay, I want to talk about JET, because JET as I said, JET is our interface to program our boxes through control plane, right? So in the next use cases you will see that how we have used our JET and forwarding plane programmability to give a complete solution to our customers, right? So JET is nothing but it's mainly you can talk about the JSD services daemon process, where our all daemons which run on Junos control plane, MGD for management, RPD for routing protocols, and DFWD for firewall, they register their RPCs to this JSD. JSD is nothing but RPC what you call arbitration. It does arbitration of RPCs, and these can be exposed to either any application running on the box or can be running the application can run outside the box. So this is the simplest idea, right? How a developer understands it, right? So this JSD, anything we want to expose, any RPC we want to expose to outside world, we expose it through JSD, and JSD has, our security, authentication and everything. So all our daemons don't have to worry about. So there's one place where authentication or security is handled. So here I want to talk about a use case. So this use case is Transponder use case, this we implemented on our ACX 6360 box. This is a transponder box. This is shipping this year, and it's generating a lot of good reviews. And here, what we did was we wanted to actually, as I said, we believe in baby steps. So this was our first baby step to see whether we actually can make whole thing work, right? So we wanted to support P4 on our box. So this was the simplest of use case. This box is basically one PFE box. So we don't have to worry about multiple PFE, multiple line cards there. So we thought, this is a good box where we can actually ship our idea and see whether it works, right? Everything, we have all the pieces available, right? So we run our JP4 agent on our FPC, and this gray area is what runs in the routing engine. Routing engine is nothing but our control plane of our boxes, right? So initial idea was that we will this transponder does not. What transponder does is cross connects to physical endpoints, like physical, let's say Ethernet to optical interface, client side to line side, right? So it just very simple, it's just physical L1 cross connect, right? So we want to expose this interface of cross connect to external world, I mean to the external controller, right? So first we did that. Then our PLM told us that that idea is good, but ultimately there will be some customers who don't want to bring in controller. So why don't you give the interface through our Junos, Juno CLI itself? So we had those we had this JP4 running, and JSD was exposing our RPCs for cross connect. Then we brought in our JET pieces, right? So JET allows you to write an application in the RE which can use the RPC exposed by any other daemon through JSD, and can handle CLI commands, right? So we just wrote another application on RE, and we were actually give this complete solution in the box itself, right? So important thing here is the CLI, which we there's a very lightweight OS running on the box, which is just handling the port, physical aspects of the system, and everything is actually done by in a way by third-party application. And the CLI, the commands or configuration is also not compiled into Junos. We have a YANG file which we just install on the CLI. It just gives you all the, once you install that, it gives you the configuration options to cross connect, right? So everything is like external package, is bring it to Junos and you run it. So this is another use case I want to talk about here. The requirement was that we have we already have our Junos boxes deployed, and customer wanted that they should be able to control all the aspects of tunneling, right? They want to use what Junos provides. They should be able to create any kind of tunnel to any destination, and it doesn't have to be one-to-one, point-to-point. Tunnel, one side tunnel can end at one gateway, other side can end at reverse decapsulation can happen from any other host, right? So we have to just give them flexibility to inject P4 program at specific points. So the RPD exposes this RPC call. So it gives nice thing that you can install the route from the control plane, but also you can give a blob, opaque blob, which can go to a data plane. So what we did was we gave the option to push P4 program in that blob, and then they are in control of everything, right? So and we don't have to say them whether you want to generate like where do you want to end the tunnel and how do you want to encapsulate. So they are in charge of everything, right? So JET plus our P4 support brought in this capability, right? So this way customer is happy that we already have all the Junos feature, but we just want to control only the pieces which we want to control, not the rest of the things. And we also in the beginning of this year we also did integration with the FRR routing stack, and this is the blog which we wrote in February. So you can go and read about it. Ultimately it's just FPM of the Zebra can actually push the routing or routing plane entries to any third-party stack. So that's what we used, right? So we worked with one person from FRR, and he did all the whole integration. We just provided support from AFI, and he was able to demo it. So this is this slide is about Juniper's contribution to the Stratum, right? So here, Brian actually announced that Juniper is part of Stratum now, but we have been actively pushing for this idea for a long time now. So it got approved this Monday, right? And then it got announced by Brian that day. So what we are contributing to Stratum is that we want to bring this flexibility of AFI model, which we have used internally, and also it in a way exposes the infra which we have been using in Juniper since its inception. These objects and how do we change them, right? So it extends it and exposes it as external for external programmability. So we are bringing in this AFI model itself, and the compiler backend also we want to open source, and also this AFI HAL layer, and one switch implementation, software implementation of the switch, which can actually realize the whole AFI model, so that to give you all the pieces to actually learn and to actually use them. So the AFI model is just an idea model. It can be used in any language. It can be realized in any language. We used Yang for the first implementation. So what we do is all the objects which we have defined. There are not many, handful of them. We define in the Yang modeling language. So that gives us flexibility that we don't have to worry about new compiler. Don't have to worry about, and nobody has to worry about the compiler. We are working with existing technologies, and they are really used by networking community, right? We use OpenConfig Yang models for GNMI, right? So why don't we treat the data plane programmability itself as a configuration, right? In a way, and then if you treat that as, then it can always stitch existing configuration to this new configuration, right? So we used Yang, and when Yang can be compiled into protobuf, and protobuf can be compiled into any language you want, and customers are people are ready to can write clients in any language. And these are our right now, before we move to the Stratum, this is where we were developing AFI and JP4 agent as open source. You can take a look at it. We have some initial demos which we have all detailed instructions we have given, so you can take a look. And thanks. So I have 4 minutes for questions. So if you have any questions, or maybe I can cover more details about AFI. Yeah, Chris.
Did I see that there was a software switch implementation of AFI? That block?
Yes.
So is that something that's going to be communicated?
Yes. So everything which is yellow, it will be part of the community.
Could that be basically supplement to the MV2 type of?
Yes.
Be a new kind of P4 virtual machine, so to speak?
Correct.
All the right answers.
Yes. So we definitely want to, because if we have this objects, we have to some way give the software version of it for people to actually see it, what's actually being done, and anybody should be able to write macro code for it or FPGA code for it, or maybe this same code can be easily be adapted to a DPDK application, right? I see it as an intermediate language, more closer to the hardware than P4. P4 definitely is a great language for communication. So I think Alan talked about that you can always describe intent in P4, but when you try to map to a particular target, every vendor has to deal with the compiler backend and struggles with the changes, struggles with how to map P4 program written by the customer who does not know how the pipeline of data plane looks like, and mapping that, right? So in these blocks, so definitely, when we give very flexible option for people to program, we definitely have this mapping challenge, right? The AFI also will have a little bit of that challenge, but we have seen that these are more closer to if you think only in terms of objects, and you know how to map an object to a API call or a set of object to a set of API calls, then you just have to push that. Right, so there's something called AFI feature. So in that feature, you can define let's say if you have a particular block in the ASIC, and you define that what that block does in terms of AFI feature. The whole AFI feature comes to the HAL layer, and whole AFI feature as an atomic unit can be pushed to your hardware, right? Yes. Sure. Sure.
So have you tried it on a, I mean, so talked about before, right? Basically, backend microcode is a little easier than putting it on a flexible SE, right? Any experience or thoughts on flexible SE?
So what we tried was, try to map this model to our Trident, not Trident, Tomahawk 3 Broadcom ASIC, right? So that's the experience we have. So we have experience of mapping this to our fixed pattern ASIC like ZX and Treo, and also experience with mapping it to Broadcom Tomahawk 3. And also, I mean, it's nothing that we reinvented anything. We're just trying to expose the similar concepts which we have been using in Juniper for since its inception. Yeah, sure.
Where in this model do you validate that the atomic model is possible, correct, valid?
Okay.
For the box.
So this compiler backend will, the backend actually does two things: the translation and compilation. Any compiler, before compiler backend has supposed to do these two things: translation and validation, right? So here, because we visualize that customer may want to write directly in the AFI itself. So once this graph is generated, we have to run this target specific validation code to actually make sure that whether this graph which was generated, which actually can be realized or not, right? That's where we run it. Okay, thank you.